Okay, so we're going to keep on going with our electrical quantities that we sort of reviewed last time. We sort of just do some questions, practice some questions, and do a few different things. So let's see if you guys remember your circuit symbols. You guys drew circuits and stuff like that way back when. But there's your basic picture for a cell or power supply. And then you got the wires coming down. You got your basic little squiggle for resistor. Hopefully some of this looks familiar. And let's just do some practice and see what we can do. So let's say we have a 12-volt power supply right here. And let's say we've got a 60 ohm resistor. Let's see how much current we've got going in and what's the power of that resistor right there. Okay, well, let's see if we can piece a few things together. So first thing, we'll look for current. Basic way to calculate current is, of course, V divided by R, good old Ohm's law. Do I have them? Yep, I got my 12 volts. I've got my 60 ohms. Got my 12. I've got my 60. So that is pretty easy, right? So of course, 12 divided by 60, that's going to be 1/5. So that'd be 0.2 amps. So I've got 0.2 amps running through that resistor. Of course, I've also got power. There's different ways we can find power, but one of the basic ways is I times V. I've got the I, found that. I've got the V, so I've got the 0.2 times the 12, and we just have to multiply the two together, and 0.2 times 12 would be 2.4, right? So we got 2.4, and of course power is measured in watts. So this is a lot of what basic calculations are like when you talk about circuitry and stuff. Like there's a lot of simple little formulas and finding one quantity after the other and piecing things together. We could even go a little bit further, you know, for example, let's say it was used for 80 seconds. Okay, so how much charge was used? Well, this kicks back to the definition of current, which is charge divided by time. So if we're looking for the charge would be I times T using the definition of current. Well, we've got the current of 0.2 and we've got the 80 seconds, so that would be 1.6 coulombs of charge were used. Okay, so you can do that, and you can even divide that by the charge of an electron and find out how many electrons were actually used. Okay, so it's all just basic different types of using the basic little equations and stuff like that. So it's relatively straightforward. Okay, let's try something else. Okay, so maybe we got a power supply hooked up to something like that. It's often a symbol for a light bulb. Okay, maybe you have a 250 watt light bulb, and we've got let's say we've got a 60 volt power supply, and I want to know the resistance of the light bulb. Okay, well, there's a couple ways we could actually do it. One way to do it would be to use the power and voltage. A lot of people would do that. They would do power divided by voltage, because that will give you your current, because current is power divided by voltage. And once they had that, they would do Ohm's law, R is equal to V over I. You could do that. That would work perfectly well. Or if you remember in the previous video, we actually spliced those two expressions together, and one of the power expressions that we had was V squared over R, and some people remember it would just jump straight to this one. It doesn't really make any difference. So if we rearrange this one, though, if we're looking for the resistance, that would just be V squared divided by P. So we've got the V squared, of course, the 60 squared, so that's going to be your 3600 divided by the 250. And we would have a resistance of around 14.4 ohms. And of course, if you would do it this way, you should get the exact same answer. Okay, so these are just reviewing some of the basic expressions that we have in simple calculations. Okay, they're usually pretty straightforward. All right, now there's other things that kick in as well. We looked at internal resistance a little bit last time. We're going to look at that a little bit more as well when we get to some other stuff, but we're going to look at something a little bit in terms of combining resistors. Instead of just always having like one resistor or one light bulb, it's really common in circuits to have multiple things. So we need to look a little bit at putting resistors together and that type of stuff as well. So we'll review some other fundamental ideas and then keep on going. Okay, so another little idea that we're going to kick around before we get into major circuits and all that kind of stuff is actually we're going to use this guy right here. Let me bring this guy in. All right, there we go. Okay. Here we have a little picture of a cell. Now, if you guys remember, there's a difference between a cell and a battery. 1 unit of electricity for chemical energy, that is a cell, like this guy right here. Hence, one of the most popular brands in the world is Duracell, not Dura Battery. And a battery is actually a bunch of these guys put together. So if you have one of these guys, that's a cell. If you've got 2 or 3 or 4 or 5, that's a battery. So that's why like a 9 volt is a battery, because there's actually 6 little guys similar to this inside of that little box structure. Anyway, but we were in the last video, we talked about internal resistance a little bit in wires. And in the questions that we just did, we didn't talk about EMF, we just talked about voltage. Because voltage and potential difference is a much more common measurement to use than just straight up EMF. And there's a reason why. Now, for this guy right here, if this is like a regular AA or AAA or CD, on the side of it, it'll often be written as 1.5 volts. And that's the voltage of the cell. Now, specifically, that is the EMF. That is the ideal voltage for this thing. But the chances of actually getting 1.5 volts out of it is actually really, really, really rare or almost impossible. That's because a way to think of it, there's a reason why I have this picture here, this middle part cut in or cut out. Here is, think about it this way. Think about, there's my little symbol for a cell. That 1.5 volts, that is that right there. But by the time the electricity goes out this end or this end, it's gone through resistance. There's actually resistance within the actual cell itself. So that 1.5 volts might exist. That EMF of 1.5 volts might actually exist, but it's inside. And by the time it actually gets outside of it, there's internal resistance. And that's what this is right here. That symbolizes that. Often for internal resistance, you'll use a lowercase r. So that internal resistance of the cell is going to take away some of the energy. So by the time it actually gets out, you're not going to read 1.5 volts. If you actually hooked up a voltmeter to this thing and you attached it to the ends, something like this, and you hooked up to a voltmeter, you might only get like 1.45 volts, and that's the real thing. Well, this is often referred to as the TPD, or total potential difference, and that's what you actually get to use. So let's relay things out here a little bit. Okay, so you have the EMF. This is the ideal, perfect voltage. That's what that is. But you also have the TPD, or total potential difference, and that is your potential difference word. That's voltage. That's what we use in the Fields 1. This is what you actually use. A nice way to think about it is the EMF is the force, and the force is in the word. The TPD is sort of like the net force, what you actually get to use. So when you actually measure the voltage, stuff like that, it's the TPD, the actual voltage you want to use. That's what you actually have. So you often, when we talk about circuits, we often talk about voltage, voltage, voltage. Well, we're typically referring to that TPD is what we're actually referring to. And when you do, especially very sensitive electronics, that type of stuff, just using the voltage that's stamped on the side of the battery or the cell or the power supply that you're using isn't good enough. You actually need to measure the actual voltage that's actually coming out of it, so you can actually know exactly how many volts you're actually getting to actually use. And that's sort of the difference between EMF and total potential difference. And that's why you often hear us talking about just potential difference or voltage rather than EMF, 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 because actually getting to use the EMF is really rare. So that's why we just typically talk about the voltages and circuits and that type of stuff. Okay, even when we're just doing basic circuit practice and stuff like that, well, we may just, you may be thinking about it as the EMF, TPD going back and forth. It's not that big of a deal, especially for the basic stuff that we're going to be looking at. But it is important to realize it does exist. And when you are actually asked, EMF or total potential difference specifically, you should know there's actually a difference between the two. And especially for some of you, I'm sure we'll go into something involving electronics or electricity in some way. Knowing the actual difference and making sure you actually measure it. Like when you got a power supply, I've got lots of power supplies in the lab and they say 200 volts. I've never once actually had a measurement of 200 volts from those 200 volt power supplies ever. Like 195, 202. That's kind of weird for it to be a little bit higher, but it has actually happened on occasion, which means the EMF is actually higher than it should be. But typically it's lower, like even by a couple percent, which can make a difference with certain things. So it's always a good idea to actually measure, and we'll use often the terms get used interchangeably, but that's why we typically just talk about voltage or potential difference rather than the term EMF. So let's sort of show you the difference that we're talking about. Maybe we got like maybe like an electric flashlight or something like that. There we go, nice little flashlight, and they're shooting off light or something like that. There we go. And if we look on it, it's stamped on the side. It says 3.6 volts is stamped on the side. Well, that should be the EMF. And we actually take a couple of measurements of what's actually going on inside of our flashlight here, and we find out, if we actually take some measurements, that in the circuit there's 1.6 amps is actually being used, and let's say there's a 5.4 watt bulb that's actually being used. So we want to know how much internal resistance is there in the system, and keep in mind, like it's little tiny r is often used for internal resistance. Well, if we sort of do some calculations to figure it out, let's look at what we're actually getting to use. We're actually using 1.6 amps. We're actually using this. So let's see if we can find out the actual voltage that's actually being used. And with power and current, that would be the power divided by the current. And if I divide 5.4 watts by 1.6 amps, I get 3.375 volts. So this is the voltage that I'm actually getting to use. This is my TPD. This is my total potential difference. So I'm supposed to have 3.6, but I'm only getting 3.375 due to internal resistance. So if we want to look at that, then, well, let's see, we're losing approximately 0.225 volts to internal resistance. So that's the voltage of my internal resistance. So then what I could do is to find resistance, that's just Ohm's law, V divided by I, and it'd be the voltage lost on that little internal resistance, so that voltage right there, and I divide it by the current that's going through the system. So 0.225 volts divided by the current, and I get about 0.14 ohms of internal resistance. So of course, in a real system, that'd be the entire internal resistance for the wires and the cell and whatever, all of it put together. But that's the basic idea. So between EMF and TPD, you have the voltages that are stamped, and often that's just what we're going to be using. We're not going to worry too much about internal resistance. But if a question or a situation does, actually mention total potential difference and EMF and the comparison internal resistance, this is sort of how it works. Okay, so you just look at the values you actually have, the actual power you're using, the actual current, the actual whatever, and you can figure out how much you're actually missing, because that's probably the stuff that's being gobbled up by the internal resistance.